Welcome to our exploration of Galileo's law of odd numbers, a fascinating concept in the study of falling objects. Before we dive into Galileo's law, let's briefly recall that the equations of motion in physics describe the behavior of physical objects as they move through space and time. These equations relate quantities like displacement, time, velocity, and acceleration. Now, let's turn our attention to Galileo Galilei, one of the most influential scientists in history, who made significant discoveries about falling objects. Galileo's law of odd numbers states, the distances traversed during equal intervals of time by a body falling from rest stand to one another in the same ratio as the odd numbers beginning with unity, namely 1, 3, 5, 7, and so on. In simpler terms, this means that if we divide the total falling time into equal intervals, the distances covered during each successive interval will follow the pattern of odd numbers. Let's visualize this concept with a falling ball. We'll divide the total time of fall into equal intervals. Let's call each interval 1 second. As the ball falls, we'll mark the distances it travels during each interval. Watch how the ball falls. During the first time interval from 0 to 1 second, the ball falls a certain distance. Let's call this distance 1 unit. During the second time interval from 1 to 2 seconds, the ball falls 3 units further. During the third time interval from 2 to 3 seconds, the ball falls 5 units further, and during the fourth interval from 3 to 4 seconds, it falls 7 units further. Notice the pattern: 1, 3, 5, 7, the sequence of odd numbers. Now, let's prove Galileo's law mathematically. For a body falling freely from rest, we can use the equation s equals 1/2 gt squared, where s is the distance, g is the acceleration due to gravity, and t is the time. If we consider the total distance, d total, traveled by the body by the end of n time intervals, with each interval being of duration t, we get d total equals 1/2 g times nt squared. Now, let's calculate the distance traveled during each individual time interval. For the first interval from 0 to t, the distance d1 equals 1/2 gt squared. For the second interval from t to 2t, the distance d2 equals 1/2 g times 4t squared minus 1/2 gt squared, which simplifies to 3 times 1/2 gt squared. For the third interval, d3 equals 1/2 g times 9t squared minus 1/2 g times 4t squared, which simplifies to 5 times 1/2 gt squared. And for the fourth interval, d4 equals 1/2 g times 16t squared minus 1/2 g times 9t squared, which simplifies to 7 times 1/2 gt squared. Let's extract the key values from our calculations. First interval, d1 equals 1 times 1/2 gt squared second interval, d2 equals 3 times 1/2 gt squared third interval, d3 equals 5 times 1/2 gt squared fourth interval, d4 equals 7 times 1/2 gt squared. Looking at the coefficients, 1, 3, 5, 7, we can clearly see the sequence of odd numbers that Galileo observed. More generally, for the nth time interval, the distance traveled is dn equals 2n1 times 1/2 gt squared. This mathematically proves Galileo's law of odd numbers. The distances traveled during consecutive equal time intervals by a falling body are proportional to the sequence of odd numbers, 1, 3, 5, 7, and so on. Let's visualize Galileo's law one more time with a clearer demonstration. Here we have a ball falling from rest with time intervals marked. As you can see, the distances traveled in each time interval follow the pattern of odd numbers. In the first interval, the ball traverses 1 unit of distance. In the second interval, it traverses 3 units. In the third interval, 5 units. And in the fourth interval, 7 units. This elegantly demonstrates Galileo's genius in observing a fundamental pattern in nature, that for a body falling from rest, the distances covered in equal time intervals are in the ratio of consecutive odd numbers, 1, 3, 5, 7, and so on.